Okay, so today we are talking about how to find the key attributes and graph general rational functions. And so, what I mean by general rational functions is you can't use transformations on these. It's not just a transformation of 1 over x. We've got quadratics on top, we've got quadratics on bottom, we've got linears over quadratics, and then a cubic over a quadratic. And so whenever you see a situation where you've got quadratics in the rational function and you can't use transformations, you're going to have to use a completely different method to find horizontal asymptotes and vertical asymptotes, but the x and y intercepts will be the same. This will be a lot more algebraic than using the transformations. And so we're going to start by talking about the horizontal asymptote, how to find a horizontal asymptote. So when we were using transformations, we would keep track of how much the function moved up and down. We can't use transformations anymore. So now we're going to look at the degree of the numerator versus the degree of the denominator. And so just a reminder that a degree is the highest exponent in a polynomial. And so, for example, a quadratic would be degree 2. And then a linear, where you just have x, is degree 1. Okay, and then after you look at the degrees, you're going to eventually look at a coefficient for one of the cases. And the coefficient is the number in front of the variable. For example, if I had 3x squared, the coefficient would be this 3 right here, the number in front. So we've talked about that, but just a reminder. And so there's 3 different cases. The degree of the numerator could be the same as the degree of the denominator. The degree of the numerator could be less than the degree of the denominator, which means it's bigger on bottom. And then the degree of the numerator could be larger than the degree of the denominator, meaning it's bigger on top. Okay, so if they're the same, meaning you have a linear over linear or a quadratic over a quadratic, this would be a situation where they're the same. Okay, x squared, both of these are degree 2 over degree 2. And so if they're the same, you are going to divide the leading coefficients. Okay, and so the horizontal asymptote, remember, is always a y equals equation, no matter what. Okay, and so y equals, and then how you're going to get the horizontal asymptote in this case is you're going to take the coefficient of numerator divided by the coefficient of the denominator. Okay, so for example here, the degrees are the same, both degree 2, and so we divide their coefficients. So 3 divided by 1 would be 3. So y equals 3 would be the horizontal asymptote for this case. For number 2, we have a linear over a quadratic. Those are not the same. Here we have degree 3 over degree 2, still not the same. Okay, and so that's if the degrees are the same, you divide the coefficients. In the case where the degree of the numerator is smaller than the denominator, meaning it's bigger on bottom, we have y equals 0. Okay, if it's bigger on bottom, like we have here, we have a linear, a degree 1 over a degree 2. It's bigger on bottom, so y equals 0 automatically, even easier than the other case. And the third case is if it's bigger on top. Okay, so bigger on top, here we have degree 3. It's hard to see on this copy, but hopefully you have your own copy that you're writing on. Degree 3 divided by degree 2. So it's bigger on top And so in this case, it does not exist. D&E stands for does not exist. You do not have a horizontal asymptote. So what you would say for this one is horizontal asymptote does not exist. Okay, and so there is an acronym you can use to remember these three cases. It's a really weird, funny acronym, but it really helps kids remember. I'm gonna turn it sideways because it's long, but it's Bobo, Bot, D needs, DC. Bobo, Bot, D needs, DC. And what it stands for is bigger on bottom, and this last O is a 0, y equals 0. Bigger on bottom, y equals 0. That's Bobo. The Bot stands for bigger on top, bigger on top, does not exist. And then here, this stands for all the same divide coefficients. So Bobo, Bot, D needs, DC. Bigger on bottom, y equals 0, automatically is your horizontal asymptote. Bigger on top, it does not exist. And if they're the same, you divide the coefficients. Okay? And so that's how you find the horizontal asymptote. And the way I remember to use this funny acronym is that horizontal asymptote is abbreviated HA, like ha, like ha. So you find the ha by using the funny acronym. Okay? And so for vertical asymptotes, it's the same way we find our domain restrictions. You're looking for what values of x makes the denominator equal to 0. And so if you want to find the vertical asymptote, you just set the denominator equal to 0. And so we're going to determine the domain of each rational function, then find the vertical asymptotes of each rational function. So find the domain, which we've done before, and then find the vertical asymptotes. We're basically finding the same thing. So in number 1, you set this denominator equal to 0 and solve for x. Sometimes it's easier, you can do it in your head, which we usually do, but I'm going to write it out. And so x equals 2. Okay, so at x equals 2, we have a vertical asymptote. And so if we were to write our domain, we would say all real numbers except x cannot equal 2. Sometimes they don't write this all real number symbol, they just write the x can't equal 2. So just be prepared to recognize that situation. The other way is using interval notation, meaning we're going from negative infinity to positive infinity, but we have to skip over this 2. And so we do parentheses, and it has to go in this order: negative infinity to 2, union 2 to infinity. Y'all seen that before. And so that's interval notation for the domain. Okay, so we have to skip over the vertical asymptote. When they're asking for the vertical asymptote, don't put a slash through the equal sign, because that's actually the equation of the asymptote. It's a vertical line right through x equals 0. Okay, so for number 2, I'm going to separate this. For number 2, there's a quadratic on bottom. Okay, so we have to factor that. We're going to end up with 2 vertical asymptotes, and that happens because now we've got quadratics going on. So that's a difference of squares. So I'm going to go ahead and write x squared minus 4 equals 0. That's a difference of squares that factors to x plus 2, x minus 2. And so if we set this equal to 0, we get x equals -2. If we set that equal to 0, we get x equals +2. So those are our two vertical asymptotes. Anytime you have a quadratic on bottom, you're going to have two. Okay, so vertical asymptotes. And so that means our domain restrictions, we've got two of them. And so for our domain, we have to skip over both of those. And so if we're using interval notation, we have to go from -∞ to -2, union, -2 to +2, union, 2 to infinity. You've got to skip over the -2 and you have to skip over the 2. And so you have three intervals, the outside intervals and then the interval in between. And you're going to be able to see this clearer when we start graphing them. So there's our domain. The lazy way to say this is x cannot equal -2 or 2. Be able to recognize both notations because you may have to use both notations. Okay. So for number 3, we have another quadratic, but this one factors to x plus 1, x plus 1. I don't know why I'm using red. X plus 1, x plus 1. And so even though we have a quadratic on bottom, when we set it equal to 0 and solve, we only end up with 1. So I know I just said if you have a quadratic on bottom, you're going to have two vertical asymptotes, but this is a special quadratic. It's a perfect square quadratic that has the same two factors. And so if you see that it's a repeated factor, you're going to only have one vertical asymptote. So there's our vertical asymptote, and then our domain would skip over that. Okay, I'm going to keep using interval notation because that's the harder one to use. Okay, so skip over the -1. Remember, the -1 is always right next to the union symbol and you're using parentheses. -∞ is always far left. +∞ is always far right. All right, on number 4, we have a linear on bottom. So that ends up, if we solve it, giving us -2/3. So you don't always get a pretty number for your vertical asymptote, but you can still graph that. You did that with transformation. So there's our vertical asymptote. I'm going to go ahead and keep finding the vertical asymptotes. This factors to x plus 3, x minus 3. And so x equals 3. And x equals, well, -3 if I'm going in the right order. And x equals +3 are our two vertical asymptotes. And then here, we can't use the shortcut to factor. So we have to multiply a times c, gives us -6. Looking for two numbers that multiply to -6 and add to 5. Multiply to -6. Okay, so in order to multiply to negative, one of these numbers has to be negative, so 2 and 3 won't work. And we would want the 1 to be negative to add to +5. So you split the middle, -1x plus 6x, and then factor by grouping. For here, we can factor out a 3. And so x plus 3 is one of our factors, and 2x minus 1 is the other. And so one of our vertical asymptotes is x equals -3. The other is x equals +1/2. Okay, so the purple in each case is our vertical asymptotes. Here we had a quadratic, so we had 2. Here we had a quadratic, so we had 2. Here we had a linear, so we had 1. Okay, and so once you have that vertical asymptote, that is your domain restriction. Vertical asymptotes are your domain restriction. And so our domain here, -∞ to -2/3, pick back up at -2/3 to infinity. Here we've got to skip over the -3 first. You got to go in order. So from -∞ to -3, union, pick back up at -3 and go to +3. union, pick back up, 3 to infinity. You have to go from least to greatest in all of these. Okay, and then the domain here, you'd have to skip over the -3 first. I'm running out of room. Union, -3 to +1/2. Union, 1/2 to infinity. Okay, so that is how you find the horizontal asymptote. You use a funny acronym. And then for the vertical asymptote, you set the bottom equal to 0. And then in green, we found the domain, because once you have the vertical asymptote, you have your domain restrictions. You know exactly what to skip over. On the back of the notes, we are going to review how to find x and y intercepts and start putting all of this information on the graph so you can see what these kinds of functions look like.